Alright, let's get this. It might be a long video. Might be. So, alright, so we're going to go in detail, or I'm going to go in detail, and hopefully you follow along. What is a rational number? Well, we talked about in class, rational number is any rational number can be expressed, a number that can be expressed as a ratio of two integers, right? In this format, right? So, for example, right, written like that, right, where b is not equal to 0. So I'm going to say b cannot be 0. So as long as I can write it as a ratio of two integers, right, in the fraction format, and the denominator is not 0. What is an irrational number? An irrational number cannot be expressed in such manner. Cannot be expressed as a ratio of two integers. Right? So one can and the other cannot. And we'll talk about more in detail as the video goes along. So that's my definition. And then also in class we said, hey, another way of thinking of it is it can, as a rational, it can be written as a fraction. Right? Which is basically what I just wrote at the bottom. It can be written as a ratio of two integers. So let's take a look at the following numbers, and I'll go one by one. And if you have a calculator handy or a website that has a calculator, you can use it. 1.495. So 1.495, it's a repeating number. So this guy is this, and it's 495, 495, 495, forever and ever, repeating, right? And non-terminating. So it repeats forever, 495. And we talked about that, and we can actually set up an equation. Remember, we can say x equals 1.495. How many digits are repeating? 3. If there's 3 digits repeating, we want to multiply both sides by 1,000, right? So x times 1,000 is 1,000x. And I'm going to multiply this by 1,000. So, sorry, let me just write a few more. All right, if I multiply this by 1,000, means the decimal moves to the right 3 over, and we get, right, so imagine 1.495, 495, etc., etc. If I multiply, if you take the calculator move and multiply by 1,000, this decimal moves 1, 2, 3, and then it becomes 1.495, sorry, it becomes, oh no, where are you? Okay, it becomes 1,495.495, etc. 1,495, 1,495.495, 495, and 495, etc. Now, the 495 is the repeating parts. If you start subtracting, right, that's going to subtract, and subtract. Everything's going to be 0, 0, 0 to the right side of the decimal. And we're going to have 999x equals 1,494. We're going to divide both sides by 999. X equals 1,494 over 999. So, was I able to take this repeating decimal and rewrite that as a ratio of two integers? So 1,494, just divide by 999. If you take that, if you take this fraction to calculator and divide it, you get this repeating decimal. My point here, and I'm going to go over this process of changing a repeating decimal a little slower, but my point here is, was I able to change a repeating decimal and rewrite a repeating decimal, represent 1.495 repeating as a ratio of two integers, aka a fraction? Was I able to? Yes. And if I can, then 1.494, guess what, is a rational number. So anytime I can take a number and rewrite it and represent it as a ratio of two integers, right, as a fraction, then it's a rational number, right? So a fraction is a representation, right? It's a relationship between two integers. Okay, so 1.495 is a rational number. Let me erase all this. Okay, so I can put 1.495 on this side of the world. Cube root of 64. Is there a number? Same number multiplied by itself 3 times. That gives me 64. Yes, there is. Well, the cube root of a positive number, first of all, is positive. So it's 4 times 4 times 4, which is 64. So the cube root of 64. So that's just another way of saying 4, right? These two mean exactly the same thing. Cube root of 64 and 4 have the same meaning. And 4, we know, is a rational number. So let me put cube root of 64 on the rational side. 2.4, negative 2.4. Negative 2.4. Can I write that as a fraction? Well, the 4 is in the 10th place, and then we put 24 on top. We can simplify. This can be, but we can simplify 12 over 5, right? And then that we can change that to a mixed number, etc. But before, we don't even have to do that. My point is, can you take negative 2.4, which is a terminating decimal, it's a decimal that ends right here, right? Doesn't go forever, doesn't repeat, it's just negative 2.4, and write it as a fraction, as a ratio of two integers. Was I able to do that? Yes. In that case, it's rational. Square root of 45. Square root. So we're looking for a number. So think about it. Another way of thinking about this. Here's a square, right? That the area is 45. Is there a number times the same number, right? That multiply gives you 45. Is 45 a perfect square? Go through your list in your notebook. It would be 1, 4, right? The perfect squares: 9, 16, 25, 36, 49 is the next perfect square. So square root of 49, if you imagine a square whose area is 49, the sides would be 7 and 7, because 7 times 7 is 49. By 45, it's not a perfect square. If it's not a perfect square and you take your calculator and you put square root of 45, your calculator is going to currently say 6.08203.932 ... Right? So it's a decimal that doesn't repeat. It goes on forever. Right? And it's not a perfect square. There is no whole number or integer, I should say, that multiplied by itself again gives you 45. And if you took 6.708203.92 and you multiplied that, right, by itself, and I'll do that in the calculator, times the same number, your calculator, well, actually that's not, calculator is going to round it to 45, but it shouldn't. But it's going to be, I don't know, something like 44.9999 and then some other numbers in the back. So let me actually see if I can do that in a bigger calculator. 6.70. Sorry, I have a calculator here. 203932 times itself equals, I don't want to use the yellow calculator, I'm asking. So if you took that and you multiplied, look, you would actually get 45.00. I know there's a bunch of zeros. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And look at that. There's a 3 at the end. And then it stops there because the calculator ran out of room, right? But it's not 45 exactly. So square root of 45, number one, it's not a perfect square. Right? Square root of it's not a perfect square. It's a non-terminating, meaning a decimal that goes on forever and ever. Non-terminating. Does it repeat? No, it doesn't repeat. Non-repeating. So it's two things. And I can't write something that's 6.7082 0.03932 dot dot dot, because it goes on forever. I don't know what the last place value is. Remember how we change a decimal to a fraction? I need to know that place value so I know what, if it's a 10 over here, if it's 1,000, right? If it's 100 or whatever the place value at the bottom is, I can't write it. I can't, because this doesn't stop. It goes on and on and on and on. So I can't write an exact relationship of two integers. I can't change this into a fraction. And if I can't write it as a ratio of two integers as a fraction, then it's irrational. 13 over 27. Well, that's 13 over 27 is already written as a ratio of two integers. So no comments. Next one, next number, 8.454545. First of all, be very careful. This is a decimal that ends right there. It's not a repeating, because if it was repeating, we would write it like this, right? So it's not repeating. It's a decimal that ends right there. Can I rewrite that as a ratio of two integers? Yeah, I can. I know what this place value is. Well, let's see, 10, 100, 1,000, 10,000, 100,000, a million. So the denominator is a million. And then the number on top, it's 845, sorry, 845, 45, 45, which it would be 8,454,545 over a million. So was I able to change this and express it as a ratio of two integers? Yes, I was. So 8.454545, which is not a repeating number, right? It's just a terminating decimal. It doesn't go on forever, right? So that becomes a rational. The next number, 34.238733849029, goes on forever and ever and ever. And again, does it end? No, it goes on forever. Does it repeat? No. So therefore, it qualifies as a irrational number. Okay, non-repeating, and let me just write this: non-repeating. If it doesn't end and it goes on forever and ever, and it doesn't repeat, it belongs over here. Square root of 144. Is there a number times itself that gives you 144? Yes, there is. It's 12. So 144 is a perfect square. A perfect square goes on this side, because 144 is the same thing as saying the number 12. And number 12 is definitely rational, right? And negative 23. Again, here's negative 3 and 3. Can we write it as a fraction, as a ratio of two integers? We can. There we go. Negative 23 over 1. And that makes negative 23 go this side. You really need to know what a rational and an irrational number is. Okay? Rational numbers, again, can be expressed in this format, right? As a fraction, as a precise relationship between two integers, okay? So every single number on the left side can be written as a fraction, right? The ones on the right, the non-perfect squares, non-perfect cubes, the decimals that go on forever and ever and never repeat, they're all irrational, and I have no way of changing any of these numbers that are irrational into a fraction. Okay? You have to. I can't express how much you need to make sure that you understand the definition of rational and irrational. Here's a playground. It's in the shape of a square, so do yourselves a favor, draw the square so you can understand it. Playground where your little brother and little sister goes to play in the park. Pretty big. And they're saying that's 425 feet squared. Right? Feet squared. So, and they're asking, hey, what does this side measure? Well, if it's a square, first of all, you know that this side and this side, and actually all four sides, they all measure the same. Well, you got to figure out, is 4,025 a perfect square? If it's a perfect square, we know this is going to be a nice, pretty whole number, integer, that we're going to put over here and over here. And this is a very easy problem. I mean, it's a calculator problem, right? So let's figure out, is there a square root of 425? 4,225. Well, play with some. Well, obviously, I would choose, I don't know, let's try 20. 20 times 20, you know, is 4. Sorry, not 20 times 20. Well, let's try 50 is a little bit too little, because 50 times 50 is 2,500, right? So that's too little. So let's try 60 is 36. 70 would be too much. Let's try 62. Let's see if this is 62 and this is 62. So let's just try. So if you multiply 62 times 62, 3,844. Oh, actually, you can just find the square root. What am I doing? Sorry, 4,000. Square root of 4,225. Look, the calculator gives you the answer. So all this was not necessary. 65 times 65 is 4,225. So this would measure 65 feet. If you went to the park, and this would measure 65 feet. So that tells us that 4,225 is a perfect square, because there are, right, the sides can come out to two nice whole numbers in this case. Right, so square root of 4,225 is 65. So the answer to this question is just 65. One side of that playground that is in the shape of a square measures 65. I think I made that mess out of that problem, but it was just finding the square root of 4,225. Change the following to fractions. Okay, 1.34, and again, look at the place value. The 4 is in the hundreds. Put 134 on top. Can you simplify this? Yeah, we can. We can write it as a mixed number. Look at your multiple choice. Is your multiple choice answers written as improper fractions, as mixed numbers? So if you change this to a mixed number, 100 goes into 134. 100 one time. 34 left over 100. We can definitely simplify that, and that becomes 1 over 1 and 17 over 50. Final answer. And if it's not written that way, it's going to be written as 67 over 50. So it's either written as a mixed number or an improper fraction. But either way, that's the process. 0.03404. Let's change that to a fraction. Okay, so 10, 100, 1,000, 10,000, 100,000. So our place value at the bottom, so the denominator, is going to be 100,000. And the number on top is going to be 3,404. You can tell your calculator to simplify that, and I'll do that for you, those of you. 3,404 at the bottom is 100,000. 1, 2. Enter. Oh, shoot. Sorry. Let me do that again. I pressed the wrong button. 3,404. At the bottom is 1, 2. Simp. Enter. It's giving me a domain error for some reason. Well, you can simplify. Let's take. I'm going to divide that by 2. I don't know why my calculator is giving me a 1702, and this is going to be 50,000. It's divisible by 3, 50,000 now, so I'm just continue to divide by 2. 1702 divided by 2 is 851 over 25,000. 914. No, so this looks like the simplified version. Okay. 0.755 is just simply 755 over 10, 100, 1,000. We can definitely simplify that. Divide top and bottom by 5. And you get 151 over 200 simplified. Okay? But, no buts. That's just it. Solve and check the following equation. So let's do this one first. And please, it's a solve and check. So you have to check. And it's an equation. So let's do the first one over here. M squared minus 45 equals 855. Remember, our goal is to have m all by itself without the exponent of 2. So let's go through the process. We need to add 45 to both sides. That becomes 0. M squared equals 900. How do I get rid of that little 2 there? To get rid of that little 2, we're going to take the square root of both sides. So square root, let me put a 2 here. Take the square root of 900. Let me put a little 2 here. those two go away, right? Simplifies to just m, which is what we want. And in this case, what numbers multiply by themselves is 900. It's an equation, so we need to put plus or minus 30 because both answers will work. Let's do a check and see if we're correct. Let's check with 30, so positive 30, so 30 to the second power minus 45 equals 855. 30 squared is 900, minus 45 equals 855. Now if you subtract, so positive 30 worked. Let's try negative 30. Well, negative 30 to the second power minus 45 equals 855. That equals to 900 because negative times a negative is positive, and 30 times 30 is 900. And you'll notice that both negative 30 and positive 30 work. So the answer to this one is plus or minus 30. If you just write plus 30, you will not get full credit. Okay. Let's do the bottom one. I'll do the cube in a second. Second one, actually, let's do all the square roots. So k squared plus 76 equals 324. We need to do minus 76 on both sides. Remember, there's a little left side, right side. That goes away. K squared equals 324 minus 76, which is 248. Oh no. Oh, that's supposed to be a minus. I'm going to ask you guys to skip. Let's hang on a second. Let me change that to a minus. Yeah, so I have to change this problem to a minus. So k squared minus, minus 76 equals 324. I'm going to change that, otherwise you don't get a perfect square. So let's do that. Change it. When you guys get the sheet, it will be minus 76. So we do again plus 76 plus 76. We get k squared. Goes away. K squared equals 400. Again, what do we do here? We're going to take the square root of that side, take the square root of that side. It allows me to simplify that. K is by itself, and square root of 400, and this one is plus or minus 20. Do a check. Let's do positive 20. So positive 20 squared minus 76 equals 324. 400 minus 76 equals 324, and you know that works out. Let's do a check with negative 20. So negative 20, put it in parentheses. Please do not write it like this, because if you do write it like this, I have to take a point away. Right? This does not. If you write it like this, it's 20 that's being raised, so that's the second power, not negative 20. So you need to put a parenthesis here. Minus 76 equals 324. 400, negative 20 times negative 20 is 400. And notice that left side equals right side. So negative 20 and positive 20 are the answers to that equation. Y squared equals 625. Again, just a repeat. So again, to get this to be y by itself, we're going to take the square root of this side, and we're going to take the square root of this side. And what number multiplied by itself is 25? So it's 625. It's 25. So plus or minus 25. Do a check. My original equation, I'm going to use positive 25 and squared and see if it gives me 625, and yes it does. And then I'm going to check for negative 25 squared equals 625, and they're equal to each other. So they both work, so positive 25 worked on the check, negative 25 worked on the check, so the answer, like I said, is positive and negative, plus or minus 25. Then we have 1 cube question, so w to the third power equals 643. So it's the same process. I want w by itself with the exponent of 1, not a 3, so how do I make that happen? Well, to make that happen, we're going to take the cube root on the left side and then the cube root of the right side. So we know that the cube root of a positive number is positive. So what number by itself, what number multiplied by itself, 3 times is 643, and that just happens to be 343. Oh, sorry. 343. 343. And I believe that is 7. Not plus or minus 7, just 7. Because 7, if you think about it, 7 times 7 times 7. 7 times 7 is 49. 49 times 7 is 343. If you did negative 7 times negative 7 times negative 7, first of all, you're going to get a negative, which is not what we want. We want positive 343. So negative 7 does not work. So for the cube root, if it's a positive, if you're taking the cube root of a positive number, it's just a positive. If you're taking the negative cube root, if you're taking the cube root of a negative number, then you get a negative answer. In this case, the answer is just 7. Do a check. Let's plug it in. So let's 7 to the third power is 343. Is 7 times 7 times 7 343? Yes, it is. And our check is good. So you're good here as well. Determine what subsets the following numbers belong to. Well, let's go to a rational number. If you're irrational, you're just irrational. There's nothing else to talk about. Irrational. Right, but if you're rational, remember, we started with the, let me write, counting, or natural numbers, however you want to call them. So that's the first one. And then after that, we added 0, and our family became known as the whole family. And then we added the opposite of the whole numbers, the negatives, and they became known as the integers. And then the fractions and decimals came along, and then called the rational. So the square root of 25 is also known as just simply 5. So where is 5? Where would you put 5? Well, 5 is a counting number, right? 5 is a counting number. 5 is a whole number. 5 is an integer, and 5 is rational. So 5, if we were to, so square root of 25 is all of them: a counting, a whole number, an integer, and the rational. Negative square root of, negative 5 over 7. Well, negative 5 over 7 is not a counting number. It's not a whole number. It's not an integer, and it's just rational. Negative 8, just negative 8. Well, negative 8 was not part of the counting and natural. It's not a whole number, but it's definitely an integer. And it's also a rational. Look in your notebooks, right? You have that. Next one, 1.0093873 goes on forever and ever. Well, let's look at this decimal. Does it repeat? No. Does it go forever and ever? Yes. So a decimal that goes forever and ever and does not repeat is irrational. So this guy here is irrational. 4.44, like that. Well, actually, I should have written, the bar on top of the 4. So another correction I have to make. But what number is repeating? Well, the 4 is repeating, so it's 4.44444444 forever and ever and ever and ever and ever, and repeats. A decimal that repeats and goes on forever and ever becomes what? It's a rational. Why is that a rational? Because, like we showed before, we can change this, right, and express it as a ratio of 2 integers. I can change that and write it as a fraction, right? Which is an exact relationship between 2 integers. So this becomes rational. So you gotta really know the difference of the decimal. Which decimals goes on this side of the world and which decimals goes on this side. Okay. And then 4.44. 4.44 is a nice decimal, $4.44. It ends right there. Right, can I change that to a fraction really quickly? Yes, I can. This 4 is in the hundreds place, and I would write 444 and then simplify. But I can express it as a ratio of 2 integers, which automatically qualifies him to be a rational number. Now, is 4.44 counting? No. Is it a whole number? No. Is it an integer? No. So the only thing it is, it's rational. Okay? You got to make sure you go over this as well. Square root of 205 is between what two whole numbers? Well, let's list are perfect squares. 1, 4, 9, 16, 25, 36, 49, let me keep going, 64, 81, 100, 121, am I missing one? 144, 169, 196, 225. So if I were to make the double line that we used to do in class, did in class, square root of 196 is here, square root of 225 is here. Square root of 96 is just a fancy way of saying what number? 14, right? They mean the same thing. Square root of 25 is just 15. So 205 is somewhere over here. The question is not saying to, well, if you were to drop it, you would drop it around here. So it's 14 point, I don't know, 0.2, 14.3. But it's between, what's two whole number? It's between 14 and 15. That's what the question is asking you. Square root of 25, if you were to put it in your calculator, well, which is what you will probably do on your test, it says it's 14.3, which is between what two whole numbers? 14 and 15. So, yeah, that's it. Change the following repeating decimals to fractions. Okay, so let me find some room here. Well, let's do 0.34, and I'll do it over here. So first thing we do, set up an equation. X equals 0. What's repeating? 34. 34, 34, 34, dot, dot, dot. Two numbers repeating, which means we multiply both sides by 100. So x times 100 is 100x. If you take this 34, 34, just write a few, right? Dot, dot, dot. And you multiply by 100. Shortcut is we know that the decimal is going to move two places over. It's going to go 1, it's going to be 2. So my answer is going to be 34.34, 34, 34, dot, dot, dot. So I'm going to put over here 34.34, 34, 34, dot, dot, dot. 100x minus x is 99x. On this side, what is going to happen to our repeating side? Everything to the right of the decimal. Next, 0, 4 minus 4 is 0, 3 minus 3 is 0. Right? It's going to be 0. And 34 minus 0 is just 34. Got the x here. Divide both sides by 99. X equals 34 over 99. So take that in your calculator and you divide. You can see that we did it correctly. 0.5 repeating. Well, this one is easy, right? So x equals 0.55555 forever and ever. It's one number repeating, so we multiply both sides by 10. X times 10 is 10x. If you do 0.55555 in your calculator and multiply by 10, the decimal moves 1 over and it becomes 5.55555. Dot, dot, dot. All this, everything to the right of this decimal is going to just be 0, 0, 0 because it's 5 minus 0, 5 minus 0, 5 minus 0. So all this becomes 0. 10x minus x is 9x. 5 minus 0 is just 5. We divide that by 9. Divide that by 9. X equals 5 over 9. Next one. Next one is, and let's just write over here. X equals 2.0456565656 repeating, right? And I'm just going to put a dot, dot, dot. And the two, how many numbers are repeating? There's two numbers repeating, so we must multiply both sides by 100. So x times 100 is 100x. And on the other side, let me just put it over here. 2.0456565656 dot, dot, dot. You can multiply that by 100. The shortcut is move the decimal 2 over. 1, 2. So our answer is going to be 204.565656 dot, dot, dot forever and ever. So let me just move this to the side a little bit. I'll rewrite it again. So we're going to write 204.56565656. Remember, when we're subtracting or adding decimals, we got to make sure we line them up correctly. 100x minus x is 99x, so that's okay. And over here, right? 6 minus 6 is 0, 5 minus 5 is 0. So 6 minus 6 is 0, 5 minus 5 is 0. So this is 0, 0, 0, 0. Be careful, 0, 0. And then 6 minus 4 is 2. 5 minus 0 is 5. The decimal, 4 minus 2 is 2. And bring that down. Divide both sides by 99. And x equals 202.52 over 99, which we could clean it up, but let's just put that in the calculator and make sure we're okay. 202.52 divided by 99, oops, 202.52 divided by 99 equals 2.0456565656565656 forever and ever. So we did this correctly. And again, just another way of telling you, right, besides you knowing how to change a repeating decimal to a fraction or a ratio of two integers, you now have proof that any repeating number and repeating decimal can be changed to a fraction. And if we can do that, right, where can we put this? We can put this, or call this, we can call these rational numbers. So decimals that go forever and ever and repeat are rational. And there's your proof. Order from least to greatest. Not too keen on this question, maybe because it's just a silly question. The calculator question, but still. So, first thing I would do, change every single number in here. Not every single number, but every single number that's not in a decimal format to a decimal format. 4 to the negative third power, right? Remember, if it's a negative exponent, we rewrite it like this, over 1. Right, so that the exponent becomes positive, and then that simply is 1 over 64. But I wouldn't write it like this because I have no idea what 1 over 64 is compared to 0.075 and compared to the other numbers here. So I'm going to go in the calculator and divide 1 by, and that's going to, so rather than that, write it as a fraction. Take that, write it as a decimal, and that number is 0.015625. That's what 4 to the negative third power is. So change that to this, and then this I wrote it as a decimal. So, very small number. The second one is already as a decimal, so I don't have to change it. Square root of 20, it's not a perfect square, so it's going to be a decimal that goes on forever and ever. So that's about, we're going to go, I don't know, just go a few decimal places. 4.472, right? And then negative 12 over 7, again, I change that to a fraction, 12 divided by 7. So that becomes negative 1.714. And I'm not going to write too many decimals, just to the thousands should be okay. That says the cube root of 28. Cube root of 28. 28 is not a perfect cube. So go through your list of perfect cubes. So we know it's going to be a decimal, again, that goes on forever and ever. So let's find the cube root of 28. And if you look at your calculator, you should get, and we're going to just write the first 3.036. And then pi, if you press pi, and then you press, well, the answer is 3.14159 ... Right, it goes on and on. And then the last one, negative 1.78. Now, if that was me, I would probably create a number line. Let's see. I'm looking at this, and the biggest number I need is a 4, as a 5. Okay, I'll make a number line. That's 5, that's 3, that's 2, that's 1, that's 0. This is negative 1, this is negative 2. And this, you can make a number line, you don't have to. Visually see which one is the smallest. That's completely fine. Let me change colors. 0.015625. So that's very close to 1 penny. It's a penny, almost close to 2 pennies. So it's right here. 0.15625. Right, which is this guy right here. Right, so I'm just gonna put this on top. Actually, I'm gonna write that this is 4 to the negative third power, right? It's equivalent. 0.075, where is that? That's a little bit to the right of this, right? That's about a penny and a half. This is more than a penny and a half, but it's still bigger. You know what? Let me write the decimal equivalent. So 0.015625, and then right next to it, I'm going to write that it's 0.075. 4.472 is right around here. That's right, which is square root of 20, and I'm going to write dot 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 because it goes on forever. Negative 1.7, well, negative 1, negative 2, negative 1, negative 1.1, negative 1.2, etc. So it's somewhere around here. 3.036, which is the cube root of 28. So it's 3 and it's very close to 3. So 3.036 dot dot dot. 3.14, 3.1415 now, which is pi. Well, it's not less than that, but so I'll put it right over here. So that's pi. And then negative 1.78, right, which is this guy right here. This was negative 1.71, so negative 1.78, it's a little bit to the left of that. If you draw a number line and you do what I just did, you can clearly see who's the smallest, second smallest, right? The number who's to the further left on the number line is always the one that has the less value, right? So, and you will put that in order. So in order, and there's your order. Smallest, and this is the biggest. Okay. For this one, you have to, again, I'm going to draw a number line. Remember, on the number line, when you place two numbers on the number line, the number to the left is always the smallest, and the number to the right is always the greatest. That's it. There are no tricks here. Negative 1.09, well, that's 0. This negative 1, negative 1, negative 1.01, negative 0.10. Negative 1.09 is right over here. Negative 1.096 is a little bit just really right next to it. So between these two, who is the greater number? Well, this is the greater number and this is the smaller number. So negative 1.09 is greater, not by much, but it's greater than negative 1.096. And that's why I use a number line. Let's do the bottom ones. Well, okay. We need a negative, so 0, negative 1, negative 2, negative 3, negative 4. Let's first change this, right? That's just, square root of 9 is 9. Sorry, square root of 9 is 3, but we're going to negate that. So this is just negative 3. So let me write that. Negative square root of 9 is right here. And then negative 3.01 is right next to it. So who is further to the left? Well, the further to the left is negative 3.0, which is the smaller number. Not by much. So negative square root of 9 is greater or smaller than negative 3.0. No, it's greater. Not by much, but it's still greater. The number on the right is always the greater on the number line. I just remember. Next one, square root of 21. Let's find out what square root of 21 is first. Square root of 21 is the same thing as 4.4582 dot dot. Well, let's create a small number line. This is 4, positive 4, and this is 5. And let's place these two on the number line. 4.58, well, it's 4.50 is right here. 4.58, which is the square root of 21, should be around here. There's where I would put square root of 21. 4.55, it's a tad smaller, so I'm just right over here. I'm going to make another line. 4.55. Right? Makes sense. Think about money, I guess. $4.55, $4.56, 57, 58. So $4.58, which is the square root of 21, right? Rounded. It's a little bit more than 4.55. So says the square root of 21 is just a little bit greater than 4.55. Negative 5 and 5/4, and then negative 1 over 3. Well, the number line. That's 0. This is negative 1. This is negative 2. I don't need any more. Well, negative 5 over 4, right? Negative 5 over 4 is the same thing as 1. Negative 1 over 1 over 4, which is the same thing as 1.25, right? That's what that equals to. And negative 1.25, well, if this is negative 1.5, negative 1.25, otherwise known as negative 5 over 4, is right here. Negative 1.3, well, negative 1, negative 1.25, negative 1.30 is a little bit to the left. So there is. So again, remember, the number on the left is always smaller, the number on the right is always bigger. So how would we complete this sentence? We can say negative 5 over 4 is greater than negative 1.3. Okay? Number line does help. List the first 10 perfect square. That's kind of silly. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. And you know that we can go on and on and on, but it's just asking for the first 10 perfect squares, right? So again, every single number here, if you took the square root of any of these numbers, you would get a nice whole number, right? Perfect cubes, right? Squares. Let me go back to the square root for a second. Square root of 100 is 10. Remember, 10 times 10 is 100. 49 would be 7 times 7. Would be 7 because 7 times 7 is 49, and etc. Now in the cube, we're looking for the same three numbers, right? Perfect cubes. Nice integer that multiplied by itself gives you the following numbers that we're going to write right now. 1, 8, 27, 64, 125, that's 5, 216, 343, 512, which is 8, 729, and then 1,000. Right, so if you took the cube root of any of these numbers, right, the cube root of, for example, 8, it would be 2, right, because they're looking, because 2 times 2 times 2 is 8. The cube root of 729, the cube root of 729 would be just 9, right, because 9 times 9 times 9. So again, think of a cube, right, a cube where all the sides measure the same. Right? In the perfect cube, if you had, we're talking volume, right? The volume of this particular cube is 729, whatever inches. It means that there were 709 of these little cubes that measure 1 inch on all sides were used, right, to create one of these, and the length, the width, and the height are all the same. And that's why it's called a perfect cube. And in this case, 729 would be 9 times 9 times 9. Okay? Whew. I told you it might be a long video. 13, from the list below, from these numbers, give me 2 that you can add that give you that's going to give you a rational number, and give me 2 that you can add that would give you an irrational number. And explain. And again, you may want to put a star in here, hint, hint, on this particular question. Let's start with a rational number because that's easy, right? So a rational number. So let's think about rational number. Right, it could be a counting number. It could be a whole number. It could be an integer. It could be a fraction, a terminating decimal, right, like a 0.7, or a repeating, right? Anything that is in this will be rational. So first of all, let me take my calculator and see if I can find the square roots. 169 is 13, right? So we just wrote a list, right? So look at the list they just wrote, or the one in your notebook. Square root of 51 doesn't look like a perfect square, so I'm going to leave that out. 4 times the square root of 5 also doesn't look like a perfect square, because square root of 5 is not a perfect square root of 5 is not a perfect square, so I know it's going to be a non-terminating, non-repeating decimal. The square root of 49, I know is a perfect square, and that's give you 7. So and then square root of 2, obviously, not a perfect square as well. So first thing is to find 2 of these that I can add and gives you a rational number. Well, the first part of this problem would be if I add this and this, right, which is basically 13 plus 7, right, square root of 169 is 13, square root of 497. Does that give me a rational number? Yes, it does. Because when I add a rational number plus another rational number, it gives me a rational sum. Sum. A rational number plus a rational number will always be a rational number. Okay? And then it's asking you to give you pick 2 and explain why it would be irrational. Well, I'll pick, well, it doesn't matter which one we pick. Well, we can pick, one of them has to be rational. So either you pick 2 irrationals, like this one, 51, square root of 51 plus the square root of 2. It's an irrational plus an irrational. Or you can pick something like this, a rational and an irrational. Either one. Well, let me write irrational plus another irrational, and then a rational plus an irrational. Let me show you why, and maybe you can use it as your explanation. So, and why is an irrational plus an irrational still an irrational, which gives me an irrational number? Well, first of all, you're correct if you pick these 2. Or you could have used 4 times square root of 5, but I'm not going to use them. So square root of 51. Let me take the calculator. And again, if you take this and put it in your calculator, you know, first of all, it's not a perfect square, so you already, right from the get-go, you know that square root of 51, it's not a perfect square, meaning it's not going to give you 2 nice whole numbers that multiply give you 51. So it's going to be a decimal that goes on forever. So it's going to be 7 point, and then, you know what, let me write over here because I have clean space. 7.1414284 dot dot dot. Right, so it's a number that goes on forever and ever, does not repeat, so it's irrational. Plus the square root of 2. Let me just line it up. So it's 1.4142135 dot dot dot. Now, what do you think is going to happen when you add these 2 numbers in a decimal format? Well, first of all, I can't write square root of 51 as a fraction or as a ratio of 2 integers, so it doesn't, right? So, and I can't write square root of 2 again as a fraction or a ratio of 2 integers. So I change it to a decimal. Now, if you add this, well, if you add this number plus this number, you're gonna get right. Now let me just pick it up from here. So dot dot dot. 6 and 2 is 8. 4 and 5 is 9. 11. 4, 6, 5, 5, 5, 8. What kind of answer, what kind of sum will you get? Well, the sum that I'm going to get is going to be a decimal. So sorry, I wrote that a little too high. You're going to get a decimal. 4, 5, 5 dot. Okay, so what kind of sum is this? If you add an irrational number that goes on forever, it's in a decimal form that goes on forever and ever, never repeats, plus another one that goes on forever and never repeats, you're still going to get a decimal that goes on forever and never repeats. I don't know what that last number here is. It's dot dot dot, and it keeps on going, right? So I can add these, and now I'm gonna keep adding, right? Now keep adding, keep adding. I'm never gonna stop adding, right? So my sum is gonna be a decimal that I'm still going to be adding the place values on the right side, and on and on and on, forever and ever. So the sum is still irrational. Remember from not the previous one, or I think the before one, I showed you a special case of where an irrational plus an irrational equals a rational, but not counting that, right? Using these examples, square root 51 plus the square root 2 is an irrational for that reason. Okay? So that's an irrational plus an irrational. Let me show you what happens when if you chose a rational and an irrational, which is completely okay too. So if you chose square root 49 plus square root of 2, and you decided to use this to show me that the answer was an irrational, you would say, well, square root of 49 is easy. It's a perfect square, so it's just 7. 7 dot, and let me just write 7.0, because we know square root of 2 is going to be something else. So square root of 2 is 1. Square root of 2 is 1.414213562 dot dot dot, right? Goes on forever. What happens when I add square root of 49? Now write zeros, right? Because I can. Square root of 49 plus the square root of 2. It's a rational number plus an irrational number. Well, like I said, if you start, well, the top, they're all zeros, so 8.414213562 dot dot dot. No, battery. Will I still get a battery that goes on forever and ever? Did I say battery? No. Will I still get a decimal that goes on forever and ever and doesn't repeat? Yes, I do. So the sum of this particular rational number, 7, square root of 49, plus the square root of 2 is an irrational number, because my sum, it still is a decimal that's non-terminating and non-repeating. Okay. It is Sunday, so when you see this video, hopefully sometime Monday or Tuesday or even Wednesday, and you still have questions, hopefully you can catch me before your test. Okay, and we can go over this in class, but hopefully this helps. Next one, the laws of exponent. You're going to have 2 questions on this. Kindly just revisit. So let me do the first one. 4 to the 3rd power d. And right off the bat, the first thing you should do is put an exponent of 1 so you don't forget that there's an exponent of 1. M to the 7. All that raised to the 12th power. I'm not going to expand this and do it, but the shortcut was that when we have a power to a power, what do is the 2 powers. So the 12, remember, is going to multiply every exponent inside the parentheses. So we actually get 4 to, and 3 times 12 is 36. 4 to 36 power. D, 1 times 12, 12. So D to the 12th power. And then the M, 7 times 12 is 84. That's your final answer. And we don't have to put 4 to the 36 power in your calculator, because I don't think you're going to get one. Unless it's in scientific notation, and it is. So it's a lot of zeros. Okay? So that would be your final answer, and that would be your multiple choice answer. So again, going over this is a power to a power. So when you have a case where you have parentheses, right, and more than one factor inside the parentheses, you multiply the exponent times all the exponents inside. Let me do the one right next to it. So again, 3, and there's no exponent, so I'm going to put a 1, a to the negative 4, b to the 5th, all raised to the negative 7th power. So, just like the previous problem, take that and multiply, then you make whatever adjustments necessary. So the 3, it's going to be 1 times negative 7, it's 3 to the negative 7th power. A, it's negative 4 times negative 7, so that's positive 28. The B, it's going to be negative 35 power. That is not your final answer because you have negative exponents. So remember, we never leave anything with negative exponents, so let's make some changes here. Well, we know it's going to be a fraction because 3 to the negative 7, there's 3 factors here, right? Work on them separately. 3 to the negative 7, well, that's going to go to the denominator and then become positive. Done. A to the 28 stays up in the numerator because it's positive, so there's nothing to do. b to the negative 35th goes to the denominator and becomes positive. So that's your final answer. Everybody has a positive exponent. Could you have changed 3 to the 7th power to a nice number, 2,187? You could have. Okay, but that's not what worries me. What worries me is remembering that, for example, the 3 had exponent of 1, multiplying everything, and then taking this guy here, right, and make the necessary changes so that every factor here had a positive exponent. That's it. Don't lose points. The second one, right on top, 35 x to the negative 4th, y to the 6th, 5 x to the 10th, y to the negative 9th. Okay, I'm going to take a different colors, and I'm going to break this into 3 parts because I see it in 3 parts. The x's, the y's, and the 35 over 5. So that's 35 over 5. You put that in your calculator as it is. It just means 35 divided by 5. 35 over 5, let me write a fraction, is 7. Not 1 over 7, so don't write the 7 in the denominator because that's not where it belongs. Okay? It's 7. And if it's just 7, it goes in the numerator. So that's it. 35 over 5 is 7. If it was 5 over 35, then you would put that 7 at the bottom, right? Because it's 1 over 7. But this is not the case, so make sure you put the 7 in the numerator. That's done. Check. The x's, well, x to negative 4 travels, becomes positive, goes downstairs. X to the 10th is just positive, so it stays where it is. Let's do the y's. Y to the negative 6. Sorry, that's not negative 6. So it's y to the 6. Y to the 6 is positive, stays where it is, the numerator. And y to the negative 9, that goes up to the numerator and becomes positive. All right, so one more little step. The 7 does nothing. Let's do the x's. X10 times x to the 4th, right? Product rule, bases are the same. We keep the base and add the exponents. The y's are in the numerator. Well, they multiply each other, so product rule again. Keep the base, add the exponents. And that's your final answer. 7 times y to the 15th over x to the 14th. Last question. 15 over 20. I'm going to write it in 3 different fractions so that you know this is the same thing. Had I written this like this, it meant the same thing. And then z to negative 3. All right, let's take care of our coefficients here. 15 over 20, we can simplify that to just 3 over 4. The w's, well, first of all, let me put a 1 here. That's a negative exponent, right? So that w to the negative 5th is actually going to go down here. That's w to the first power, or just w, so let me just write it side by side like that. It doesn't travel because it's already positive. This is z to the negative, well, let's take care of the z to the 3rd power. That's going to stay exactly what it is, but this guy here goes to the numerator. Remember, you have to make the exponents positive, so it goes up. One little step more. 3/4 is done. The z's, now I can combine them. Keep the base, add the exponents, make it a 6. The w's are next to each other. Remember, they're multiplying, so w times w 5th, the same thing as w to the 6th power. This is your final answer. Your bonus point, it's not going to be a word this time around. It's going to be problem 15. Not the same problem, but it's going to be 15 and what's the other problem? What's the other number? 15 and well, it's going to be 15. Right, so I'm going to give you an extra problem. And this is going to be your bonus question. So let's do 389. You must show all the work. Right, so if you get it, great, you get 2 points. If you don't get it, you don't get 2 points. But it's going to be a number that I give you. And you're going to find the square root. Go through the process of finding the square root to 3 decimal places. So Perfect squares, 389. The biggest perfect square, well, it's not going to be 20, so let's see if 19 squared is 361. We know that 20 squared is 400, so the biggest one is 361, which is 19. So 19 is the greatest perfect square that goes into 389, which is 361. Subtract, 9 minus 1 is 8, 8 minus 6 is 2. Bring 2 zeros down, right? We're going to double the top. Remember, double 19, we got 38. Add a place value. So this is about 380. This is about 2,800. So I'm going to say 7. Remember, this number and this number have to be the same. So if I make it a 7, let's multiply that by 7. So 387 times 7 is 2,706. Yeah, 709. So it's a 7. That's a 7. 2,709. If I subtract, I get 91. Let me bring these 2 zeros down. So that becomes 9,100. I want to double the top. 197 times 2 equals 394, and add a place value right there. Let me make that purple. So this digit and this digit have to be the same. So that's about 3,940 something. How many times can that go into 9,100? That's obvious. 2 times. So 2 times 3,942 is 7,884, which you're going to subtract. You get 1,216 left over, and bring the last set of zeros down. We're going to double that the top again, so 1972 times 2 is 3,944. Place value. So our last digit, so this is about 39,440 something, and this is 121,600. So I'd say about 3 times. Right. So 39443 times 3 is about, yeah, we're close. 1,118. 329. Subtract. Oops. 118, 329 equals, and we have leftover 2,271, which we could, we can continue, but I think going 3 decimal places is more than enough. So take the calculator, find square root 389. Let's see if we're close, or actually not close. We are exactly correct. So if you take the square root of 389 calculator, your calculator is going to say it's equal to 19.7230892, and I don't know what else, but the first 3 is these 3 that we just found. Okay, so that's going to be your bonus point. Find the square root of a number to 3 decimal places. Let's do 55, just a little more practice. Okay, let's find the square root of 55 to 3 decimal places. Okay, so perfect square, 49, right? Square root of 49 is 7. Square root of 64 is 8. So somewhere between 7 and 8. So the biggest perfect square that goes into 55 is 49. So 7 times 7, 49. Subtract. That's a 6. Bring the next 2 zeros down. We're going to double 7, which is 14. Change colors. 140 something goes into 600. 1, 2, 3, 4, 5, 6 times. Because 300, no. Not 6, sorry. 4 times. Hopefully I'm correct. Remember, if that's a 4, this number must be a 4 as well. 144 times 4 equals 576. Close enough. Subtract, 24 left over, bring these 2 zeros down. Next step, double 74. If you double 74, you get 148. And please don't forget the extra place value. So think of this number as 1,480 something. This is 2,400, so it's just once. 1,481 can go inside 2,400 only one time. Subtract. and you get 919. Let's bring the last set of two zeros down. Let's double the top, 741. It's going to be 1,482, and then place value, right? Add a place value. So this is about 14,820 something. This number at the bottom is 91,900. 1, 2, 3, 4. Let's try 6. So let's, if this is a 6, this has to be a 6. Let's try it out. 14826 times 6. It's going to be 88,000. Close enough. 88,956. Yep. If you subtract from 91,900, leftover is 2,944. Let me take square root of 55 and see if the calculator says that the first 3 digits to the right of the decimals is 416. So square root of 55, and look at that. It says that it's 7.416198 But these first 3 digits are exactly the first 3 digits that we got. So we are good. So make sure you know how to find the square root of a number, 3 decimal places. So this would be your bonus question, for example, right? Let's say I gave you find the square root of 55 to the nearest. And all this will be the work that you need to provide. If I don't see any of this, because we can just easily put in your calculator, but it's not the point here. The point is to find it like we did the fun way. Okay, that's that.